Francesco Nori. So Francesco, thanks so much for coming today. Francesco is a research scientist director at DeepMind. But just because he works at DeepMind, it doesn't mean all he knows about is neural networks. Because before Francesco joined DeepMind, he had a background in robotics, so he really understands how to get machine learning working for robotics and how to get the best of both. So he worked at the Italian Institute of Technology before coming to London, and he did a lot of work in the iCubs that some of you may know about. So hopefully we can learn about how you really get machine learning to do the stuff that we couldn't do a few years ago with classical robotics techniques. And I look forward to your talk. Thanks, Francesco.
Thanks. It's good to come after Andrew because I think my talk would be very thought-provoking. We didn't have time for questions, unfortunately, because I had a few as well, and I think they are in a very grey area of where we think we should invest our energies for solving robotics. So I will present a very orthogonal view with respect to what Andrew did. I don't think that that's my way of thinking. I think there is way more into understanding a little bit more on the structure of the world and how we can use it for robotics. But I will present a very orthogonal view, which is very connected to what we're doing at DeepMind. And as Ed was saying, my personal background is in a very different part of science. I will do a little bit of intro of Google DeepMind, and I will discuss how we are tackling big problems like generate complex action, generalize complex actions, and understanding the context that we use together with these complex actions, and then we'll draw some conclusions. Just a little bit of intro for those of you that didn't know, but I was part of DeepMind, and I joined in 2017 after it was acquired by Google. But initially it was a company generated out of the Gatsby unit at UCL, and it became a startup, and then was acquired in 2014 by Google. At the same time, because of the investments in general around AI, Google Brain was created in 2011, and in 2023, a year ago, we were merged together to form Google DeepMind under Demis. It's good to bring back the mission, also the old one. This is our old mission for DeepMind, which was solving intelligence to advance science and benefit humanity. The reason why I'm bringing it up, because it will see a little bit of flavor of this mission also in the research we're doing these days. More recently, given the ChatGPT moment, our mission changed a little bit, but it still has some interesting aspects. In particular, it has changed to building AI responsibly to benefit humanity. I just wanted to stress on the responsibly. I think that's a very important topic. We'll briefly touch on a paper that touches on safety for robotics, but in general, we need to do more for sure. And that's a slide that it's a very historical one. It comes from before I joined DeepMind, so before 2017. But it represents well how we consider building intelligent beings, or an agent as is named here. We really take the approach in a very end-to-end fashion. We don't bake in too much structure within the agent or the neural network. And we start from raw observations. We want to generate raw actions. And we try to generate a variety of behaviors by having a conditioning that can come in different forms, either in the form of a reward, text, images. Now multimodality is it's a big part of what we're doing, so not just text, images, including actions as well, so condition with actions and also getting actions out. And we don't explicitly emphasize on the structure of the environment, we just care about observations and actions in their raw format. I just do this over and over again, and for this audience maybe it's not really good to remember how many achievements were obtained with this simple approach. And I'm always mesmerized, and what I do with this slide is I customize it for the audience. So today the customized part is on the top left part, where I just asked Gemini, in this case, not ChatGPT, to just become something else for me. And the something else I wanted it to become is I want you to reply my questions using words which starts only with British Machine Vision Association, BMA. And then, how are you today? I think the answer is funny as well. It's like my mood, my blues. And you can keep texting, and you will get sentences with only these letters, right? What I wanted to capture with this slide is a very simple thing, which is, I think, a big novelty of what we're doing now. The way of conditioning of a behavior is becoming extremely natural, and everyone can do it. My mom can do it, which is like the big thing that we couldn't do it 4 years ago, possibly. It's like it's a very recent thing. And you see other kind of conditioning. You can make it, transform it into a code or a software engineer, or a translator, or even ask a affordances of objects, which is more connected to what spatial AI was about. And yeah, again, a few other examples which I'm just mesmerized, and just looking at them, every time I look at them, I get some good insight on what we are after. Again, Andrew mentioned a lot of problems were considered to be unsolvable or extremely difficult to solve. This was one that to me was very difficult to solve, like generating very photorealistic images from text. And this is becoming nowadays very standard. It's impressive, I think. Another example, I will not spend too much time on it. But I want to emphasize that this works really with a variety of actions, observations, and data. This is, for example, video generation. I just wanted to touch upon a thing that is very dear to me. I think we're not putting too much structures in robotics, but I think we are learning a lot from the human brain. And something that, as a neuroscientist, I have a little bit of background in neuroscience, I was always taught is that prediction, being able to predict the future, is an important component of what the human brain does, right? So the fact that we now have models that can predict the future of an image, or simply predict the video from text, is again a very powerful tool that we should be able to use in our representations. This is probably useless. It's how much knowledge can be baked into one of these models. In particular, we participated with AlphaCode to a competition among computer scientists, and we ranked within the 54% of coders in particularly complex problems. But this is the one that is connected to robotics the most. The bit that is missing, and is also connected with what Andrew was sort of referring to, is I believe that any model would also require it has to be controllable in a sense. So this is Genie. It's a model that doesn't generate images, doesn't generate videos, but generates playable games. So it generates a piece of code that requires inputs to actually generate the output, right? In this case, it's like 2D video games. What I think is also important is to have not only generative models, but also controllable generative models. Those where you can input actions and see what is the result of your actions into the board model that you have. And that's a bit, I think, is becoming available to us. Again, this is just video games, but you can think about something way more complex. I think it's important to keep in mind a couple of things, how we achieve this. It's through evolving the kind of information and the kind of representations that we use for our deep neural networks. In the last 5 years, we had like a lot of things changing. Transformers is the greatest and the latest, but you see that there's a common theme, which is relatively inspired by the human brain architecture. We went from convolutional neural networks to attention systems and feed-forward and embeddings and so on. It's evolving, and it's a big part of the equation of how we got these results. The other one is probably the most mesmerizing, and I need to bring up the slide as well because I really love it. If I tell you that in 2 years we will improve by a factor of 2 any of the technologies we are used to, like imagine I will promise you that in a couple of years we'll have a car which is either twice faster or twice more power efficient or anything else, any of the quality indicators that we use to evaluate or buy a car, if I tell you that in a couple of years we will have a twice better car in certain parameters, you will probably go like, it's impossible, it's not going to happen. Twice faster, twice more energy efficient, no way you can do it, right? With neural networks and compute, it's not just a factor of 2, it's a factor in 20 years of 10 to the power of 15 or something like that, right, in 30 years. So it's difficult to grasp because it's a number that is unconceivable. It's very difficult to relate. And this is getting really, really, really powerful. I think we need to acknowledge that this is opening up for us as researchers like a new tool that is completely giving new results to us. And the other thing that I always mention on this slide is that we are getting close to the number of connections comparable to the number of synapses in the human brain. Of course, we're missing the structure of the human brain. We're missing many of the priors, but still, this is a fact that I think we need to acknowledge. Let's talk about robotics briefly. We are a team distributed across 3 different locations, Mountain View, New York, and London. We have a slightly different mission statement, of course, an emphasis on embodiment and an emphasis on the physical world. So we want to build a system that not just displays some AI abilities, but also in the physical world through an embodiment. How do we do this? I think something that Andrew didn't emphasize enough that I really care about is that there is a need to create more flexible, low-level skills that are essential to interact with the environment. Andrew in particular was showing some very interesting results on, and I really believe it's a good take on what needs to be done. Even with a very simple set of actions, you can do a lot of things. The video of the P2, was it called P2? PR2? I don't remember. The Willow Garage robot going around and setting up the room is a very good example. We can do probably 90% of the things we are doing. I'm also personally interested as a research scientist on way richer control skills and low-level control skills that have to do with like the way we interact with the environment, not just with a parallel gripper, but with the entire body, including our very flexible hands. And we look at the low-level skills from the lens of the generalization, being able to get enough understanding of a few of them or many of them to generalize over them. We emphasize on connecting these skills with a semantic understanding and reasoning from web scale data by using large models as a starting point for learning these low-level skills. We use a lot of teaching and demonstrations to get the data, and we have a tool called MuJoCo for generating large-scale simulations, which is open source. This is just the focus areas: mobility, dexterity, manipulation, embodied reasoning, and planning. We also work, as I was saying at the beginning, on models and algorithms suitable for robotics. We have a simulation infrastructure and a large scalable robot infrastructure for testing our ideas. How do we work with DeepMind and with sort of applications or partners outside DeepMind? We tend to see the collaboration with Google DeepMind, with Gemini in particular, with 2 different streams. On one side, we want to solve intelligence in first place as a way to solve robotics, but also we are helping Gemini to learn more about the environment by providing robotics data to improve Gemini capabilities. On the other side, we are grounding our research with applications. So we will see a few tasks that are inspired by real-world scenarios, and we are bringing this back to our research. Let's talk a little bit about how to perform complex actions. This is a little bit of history of what we have been doing. We started in 2015, just in simulation, and then progressively we transferred ideas in reinforcement learning and robotics into the real world. In 2023 in particular, we released a paper which is possibly displaying one of the best whole body humanoids skills in the field of when playing soccer. And unfortunately, I don't have a video bigger than this one because it's not loading well my presentation. But I think this is quite an idea of the kind of dexterity we could achieve. What is our current approach to learn skills? We use a lot of demonstrations. In these days, we are actually betting on very simple embodiments like the one you see there that are extremely good for teleoperation. We collect large amount of data and then we deploy complex low-level motor control skills like the one you see on the right-hand side, from folding, hanging a t-shirt actually, to tying shoelaces, to more industrially inspired tasks like the one you see there, which is like a gearbox assembly, inspired by the NIST benchmark challenge. One approach to learn complex skills is also to learn in simulation first and then transfer on the real robot. In particular, I encourage you to have a look at the OP3 videos playing soccer, because I think the dexterity that is displayed by the robot in playing soccer is extremely new, in particular, and extremely dexterous and agile. The observations that we're using in this particular behavior is just camera images from the camera mounted on the robot, so it's actually quite end-to-end in that sense. And we used a standard zero-shot sim-to-real transfer using domain randomization to robustify the policy in order to transfer it on the real robot. We also worked recently on low-level motor control skills for dexterity. We are using the DexHand, which is this hardware designed in collaboration with Shadow Robotics here in London. You see here a task that might look a little bit very simple in a sense, which is a grasp plus reorientation plus insertion of a connector. In this case, it's a 3D printed version of a standard connector from, again, the NIST board. What is surprising to me is the level of generalization you can achieve. And in this particular approach, we were again using a sim-to-real transfer approach, so a lot of data were generated in sim. The initial demonstration of the task was provided in by few demonstrations, I think just 10 demonstrations. And we used a sparse reward in training the policy with classical RL, in this case by using a filtering of the exploration through non-variance filtering, non-zero variance filtering. How can we generalize across tasks, environments, and embodiments? What we've been using is just drawing inspiration from advances in language and computer vision. So what we have done is to generate large volume of data through teleoperation in general, but also through RL. And then treating the robot control problem as a language modeling problem. So we use standard architectures where additional tokens are provided in the form of actions. And this is just a very simple way to ground language modeling to both the 3D understanding of the environment, but also the actions that are needed to execute tasks in that environment. And then we have trained and evaluated on a variety of held out tasks. This is a work that we have done a year ago at DeepMind before the merge. We have seen that there is some positive signal or positive transfer in terms of generalization. In particular, we have seen, or the most interesting generalization we've seen is that we can train on relatively simple embodiments with parallel grippers in simulation and in real, and transfer on way more complex systems like you see here a multi-finger hand with 14 degrees of freedom and independent joint control at the fingers. The other important bit that I wanted to talk about today is how do we embed common sense and general purpose reasoning in our robotic systems. It's again a very simple approach, very end-to-end. We start with a visual language model that we train on the internet, and then we just add our data from from robotics collected on our system. Again, data are executed actions specified by language instructions. And then you can get interesting generalization or actually free-form actions like the one you see here. You can talk to the robot naturally. In this case, videos are online, but you see a couple of examples. You can ask things like move the Coke can to Taylor Swift, which is a very semantic task if you want, or move the banana to the sum of 2 and 2 plus 1, just to give another example. But it's very interesting that the task specification, as I was mentioning before, can be extremely freeform. And I will just finish with a recent paper that won one of the best paper awards at IROS. This is just to say that, of course, research is very active on trying to be a little bit less end-to-end, and trying to see if there is possibility to have intermediate representations. The idea of this work was to basically start from existing techniques. I already presented this idea of having vision language action models, where we just add the additional modalities of actions into the training for large language models or visual language models. Of course, there are some cons and pros. The one that possibly is more interesting is these models are very non-interpretable. They lack of high control frequency. They're not suitable for high and fast reactive behaviors, but they are also conceptually very simple, especially for training. Another approach that we used in the past is to just use large language models to generate Python code that then is executed as low-level actions. This is more interpretable. You can bake in some semantic safety, and it works without any training. But in terms of drawbacks, there's no physical safety. It's difficult to apply it to highly textual tasks. And we recently presented a more structured approach where we have a number of layers that range from the high-level reasoning in the form of a large language model, mid-level skills that are more similar to representations like the one that Andrew presented, but in this case was mostly a point cloud representation for scene description, and then a low-level controller that can work together with the previous 2 layers in order to execute actions on different embodiments. This will leave, I hope, some space for questions. Coming to the conclusions, I think we are now exploring how deep neural network can represent complex control actions. In particular, we're implementing on these ideas on real systems, and of course, we need to add additional information with respect to the one we are gathering from the web, and large simulations, accurate simulations. We often use first-person human demonstrations, and sometimes we use multi-agent approaches to make the environment more flexible. And we are exploring how large neural networks can represent a large amount of behaviors, and see and test the power, how much these actions can be generalized. Yeah, and now it's time for questions.
Thanks very much, Francesco. So, yeah, we've got time for questions. So, anybody got any questions? Put your hand up. Yeah, Ivan.
Yeah, thanks for a great talk. So, I know the robotics community, as you mentioned, has learned a lot from other communities in AI, for example, the vision community, language community. Can you share a little bit about what findings you've made in the robotics research that will be useful to other fields of AI as well?
Yeah, it's a good question. I think one of the things that I can mention is that it's related to the spatial AI that Andrew was presenting. We know for sure that at the moment, these large models, they lack physical understanding of the environment. I think that what I presented today is a very end-to-end approach, again, to enhance large models with some physical understanding. I think there are many low-hanging fruit that will be very effective, that could really be implemented without thinking about robotics first. For example, being able to have a large models that have an understanding of distances, an understanding of relative positions between objects, but also a little bit of understanding how actions will affect an object, as I was mentioning before. There are many things that will increase the semantic capabilities of large models by just having input from other type of knowledge that at the moment we are not collecting from the web because it's not there. So I think that in that sense, thinking along the line of what is my research field, in a sense, lacking, and what is difficult to get from a large model, could basically enable a way of thinking how I can represent this knowledge in the form of data, so that I can train a model that is like covering also the kind of data that currently they are not sufficiently represented in these large models. Yeah, that's one way to look at it.
And Francesco, thank you for the talk. I'm looking into robotics as well, trying to achieve the high accuracies we need for real-world implementations. I guess one question I had for you was an end-to-end approach. Data is usually a bottleneck. Remember, Google has a lever that it can scale to billions of users very quickly, and we saw this with object detection using the reCAPTCHA. What sort of approaches do you see in terms of scaling the data bottlenecks at DeepMind using Google's levers? I know that they're recently releasing headsets that can be used to get some more data on real-world interactions. So how do you see the scale that you have as a unique lever, giving you that sort of advantage in this bottleneck?
Yeah. So maybe I'm not the right person to ask. I can answer with kind of the vibe that I feel at the moment at Google DeepMind, but I'm on a different and a slightly different. My preference will be slightly different. So at the moment, I think we are thinking about increasing, first of all, first-person demonstration. So we definitely have increasing the number of people that are operating, helping us with creating actions for our robots. We are collaborating with academia a lot to scale up as well. We're also thinking about devices that are not, they're more wearable, easy to deploy at scale in the wild. Think about, there was an interesting approach, which is like a handheld gripper, which is exactly identical to the one you have in a robot, and you just go around and do things. So there's definitely a lot of that going on, and then I think simulations is another bet that people are thinking a lot about. This is more like the standard answer that someone from my team will give you. I personally think what Andrew said is actually very true. I think that we could prove that we can really advance the state of the art in robotics by start thinking along the line of, what if I can create a simulated scene of this environment with all the objects moving, and then use standard planning and action execution algorithms to solve many tasks in the environment. I think this is very true. It's not covering everything. I would say that's a question I wanted to ask Andrew, actually. How many is left after we solve this way a relatively simple set of tasks? I think it's covering 90% probably of things we can do in the environment. There's a 10% missing. There's not gonna be as easy just because it's too control reach in a sense. You probably saw in the video by Andrew that there was a lot of planning happening, right? Humans don't do that. I'm not reorienting this laptop by first putting on the table, grasping it in a different way, and then putting it somewhere. We do way more content-rich tasks, right? But I still think that that's a good approach. Just thinking along the line of just scaling data in SIM mostly, but also in a very structured way. Don't think about solving the whole thing, but just solve the 90% task you can solve with a parallel gripper and a mobile system. I think there will be already quite a lot of data that you can generate by simply using a SIM, which is generated by a real environment and then acting in that environment.
Okay, let's just go for a question over there.
Just a quick question. So, when you were showing like the robots playing football, when you go from simulation into real world, usually I'm curious about how do you design, think about the workflow of the problem. Like, do you structure the problem in a way that the simulation training is exactly the same as the real world training, or it's a bit like you keep trying and then you see that, oh, we forgot that we have this problem, and then you add it to the simulation and you go back and forward.
Yeah. Very good question. My background is actually control theory, so that's where like my bread and butter. And I know that no policy or no controller will work without robustness around the supposedly like nominal model of your system, right? So simulation offers you a nominal model of your system, and it's very difficult to align it with reality. Reality is way more noisy. It's so very unpredictable, and it changes every day, right? In particular, the policies for playing soccer uses images from the camera in the robot and then executes actions. So it's a very end-to-end in that sense. And there's so much noise everywhere, like in the camera, in the lighting of the day, in the actions, in the actuators. You know, they warm up, they tend to be less torque, they produce less torque. So there's a lot of ambiguities. So robustness in that particular case, and I think it's a very powerful technique, comes from domain randomization. So what we actually do is expose the agent to millions of different simulations, actually an infinite number of different simulations. We sample one, we train the policy, and then we sample another one, and we try to robustify the control actions by just offering noise in the kind of environments that the policy needs to learn from. So it's actually quite robust, and you need to just find the right trade-off between robustness and efficiency, because that's like a very difficult exercise, and there are actually nice papers to find numerical ways to actually choose an optimal level of noise or domain randomization in your system. So that's actually very, I think it's one of these techniques that emerge with reinforcement learning that is very effective and relatively robust, that can be used for many actions. So all the actions you have seen actually are trained in SIM first with this approach.
And there was one question, someone put their hand up here. Who was it? Because I'm going to say time for one more. Okay, yeah, was it you? Okay, one more question. Yeah, thanks.
There seems to be like a lot of recent approaches that are training almost embeddings to query VLMs and LLMs with. So when you talk about spatial AI, I guess, or kind of this geometric understanding of the world, my question is whether, do you think that the current strand of LLMs or VLMs have that knowledge in them? We need to find the right way to prompt it. Or do we think that we need to inject that knowledge and like make the models have that understanding more holistically?
So, as Ed was saying, I'm not an expert in machine learning, but something that when I joined in 2017, is that right? What I said is like my background is not as an expert of machine learning. Which is true. I don't consider myself a person like with a background in machine learning. I'm a control theorist. I have a lot of background in robotics and hardware in robotics as well. But what I was really impressed in 2017 when I joined DeepMind is that no one was thinking about the details, how the information was represented in a neural network. We were just thinking, oh, the information should be there, and it should correlate this other piece of information. And then if I just train this way, the correlation will happen in the right way. So it was really a step up for me as a research scientist, right? So there was no need to think about the modeling or like the physics or the differential equation. It was like, no, the information is there. You correlate with this other information. And then they were building massive systems out of just thinking, what is the information that is coded in this neural network, right? So nowadays, my answer to your question is exactly this one. I think that nowadays we know VLMs, they have like a certain type of information. And we know what kind of information is in there, right? That's what I was referring to before. We know, for example, that a lot of understanding of images is there, a lot of semantic understanding, a lot of planning is in there. There's not much of 3D understanding. There's not much of understanding if I push this way, what happens, right? Yeah, a little bit, but it's not really grounded on a physical embodied systems, right? So what we're trying to do is just let's think what is the best way to inject in the form of data this information, and we're pretty sure it will correlate in the right way just because of the way we train it, right? Because of the structure, the attention, the cross attention, and the multi-layer perceptions, and so on. So we are reasoning at that level. We are really saying what is the information is missing, let's add it, and then let's just think about the problem as end to end, and the structure in the network will correlate that particular information. There's one thing that can I just use like
of
a few more
course.
minutes?
Yeah.
There's one thing that I really loved when I joined DeepMind in 2017, which is they were training a policy to just navigate a random maze to look for an apple. Okay, it's a random maze. You need to find the apple the quickest, right? That's a very simple problem. A randomized map. So what I know as a scientist is that to do it optimally, you need to do SLAM, right? You're dropping it in a room, you need to understand what you explored, you need to understand, oh, it's like I'm here, I can't go there, so I need to explore the other way, because otherwise it will not be optimal, right? So I knew that somehow that agent was doing SLAM, and it was indeed. And the way to do it was actually to be able to extract from the layers within the network, which was an end-to-end network, the information to predict a map. And it was doing it, right? So the information is indeed there. There was like clearly a SLAM coded in end-to-end, but it was not written by everyone. But the information was that it has to be there, because it has to be. Because if you see a behavior, then the information has to be there. I think that's the way we reason about the end-to-end information.
Great, thanks. That's all the time we have for questions. So, Francesco, thanks so much for your talk.
I'll stick around.
Oh, okay, great. So,
That's
before we...
nice.
Right, oh, easy. There we go.
Thank you.
We're going to break for coffee now until 11:30, and then at 11:30 we'll have a